Hello students, it is Mr. Botinsky here, and we are going to be looking at the extra practice for 7.4 today. Before we begin, we need to look at the zero product property. And so that states if the product of two real numbers is zero, then at least one of the numbers is zero. So if we have an A and a B that are real numbers, and A times B equals zero, then we know that A equals zero or B equals zero. And those are called solutions. We have seen this before, all right? So the solution part, when we were working with lines. Okay, so before we get into the problems for today, when we that say solve, we are going to go ahead and look at this. So previously, we have seen if we have y is equal to, say, x minus 3. We notice that when we write that equation, what do we get? We get this line, and it crosses the x-axis at 3. And so we get that from when we solve for x. Okay, so if y equals 0, so when y equals 0, x would equal 3 to make that equation true. And we see that here. Okay, so in we see that several places. We could do another one, and if we had y is equal to negative x plus 4. Well, if we had the negative x plus 4, we solve for x. X would have to equal 4 in that equation for y to equal 0. So we are finding times when the equation crosses the x-axis, or in other words, what can x equal when y equals 0? So we are going to be able to go into that today, and we will see that better, um, and we'll go ahead and view that here on the graph as we get into that. We are now at the top of page 222, and it says we are going to solve these equations. So we're going to do the first column and the second column, and then I will be letting you do the third column to check your understanding. So in our number 1, we have x times quantity x plus 5 is equal to 0. So for us to solve this, we have to think about when can either of those factors, and we call that factors, when can either of those factors equal 0? Well, based on that zero product property on the previous page, we know that one factor could equal 0 or the other. So possible solutions. We set each of those factors equal to 0. Well, our first one here, well, x equals 0, we just did it, okay? Like we just set it equal to 0, and we've got it. The other one, we can say x is equal to, oh, sorry, x plus 5 is equal to 0. Solving for x, we need to subtract 5 from both sides, and we get x is equal to negative 5. So we have x can equal 0, or x can equal negative 5 as our solutions to the equation. So let's look at that on our Desmos. So when we put that in, we put in that expression x times the x plus 5. What do we notice? We get this graph. It crosses the x-axis when x equals negative 5 and x equals 0. That's pretty cool. Let's look at the next one. We have a times a minus 12 is equal to 0. So here we go again. We say a is equal to 0. So that's that first factor. And then we say a minus 12 is equal to 0. To get a by itself, we need to add 12 to both sides. And we get a is equal to 12. So possible solutions are a equals 0 and a equals 12. We can see that again here in our graph. So a times a minus 12. It doesn't really like our a, so we're going to do that. As we zoom out, we have when our x equals 0, or when our x equals 12, it crosses the x-axis. So you can go ahead and try number 3 on your own. Checking your answer there, we get our p can equal 0 or p equals 2. I did change those to x's just from the standpoint of most generally we're thinking about when it crosses the x-axis, or so when y equals 0, it's crossing the x-axis. All right, let's go ahead and look at number 4 and 5, and then I'll have you do 6 on your own to check your work. We have c minus the quantity c minus 2 times the quantity c plus 1. So we're going to set c minus 2 is equal to 0. Add 2 to both sides to get that c by itself. So we get c is equal to 2. And then we take c plus 1 is equal to 0. So set the other factor equal to 0. Subtract 1 from both sides to isolate that variable c. And we get c is equal to negative 1. Or x is equal to 2 and x is equal to negative 1. Remember that variable, it could be anything you want at that point. So our next one, this one looks a little different. So this one, you could notice that you could factor out a 2 out of both of these, and it could be made simpler. But we're just going to go ahead and do it the way they have it right here, and take our factor 2b minus 6 is equal to 0. What would we do? We would add 6 to both sides, get 2b is equal to 6, and then divide both sides by 2. So we find b is equal to 3. Then we take our 3b plus 18 is equal to 0. So we're setting that factor equal to 0. Subtract 18 from both sides. We get 3b is equal to 18. divide both sides by 3, and we find b. Oop, that's a negative 18 right there. When we get b is equal to a negative 6. Let's go ahead and look at the graph of that one, just because. So we have quantity 2b minus 6 times the quantity 3b plus 18. I'm actually change those variables to an x, just because Desmos really does not like those more strange ones. And then look right here. We have this graph. It crosses at x equals negative 6 and x equals positive 3, which is exactly the solutions that we found when we solved this. So when you're taking a state assessment, and if you need to do this quickly, this is a really convenient time to be thinking when it asks for the roots. If you're able to factor something or able to graph it, what can you do? You can just go ahead and put it into a graphing calculator and see where does it cross the x-axis. And then you have your roots. You have where it crosses, and you're set. So try number 6 on your own right now. If you're just joining back with me, you'll notice that you get s is equal to 3 over 5 for both of those. So we have a double root at 3/5. Let's look at how that looks on our graph. So we can go ahead and type this in to Desmos or whatever graphing utility. I'm going to replace the variable s with x. And let's see what happens. What happens when we have a double root? What we notice, okay, we can scroll in right there. 0.6. Okay, remember that is what 3/5 would be as a decimal. Okay, is 6/10, or so that's 3/5. So notice that that's actually going to be the vertex of that parabola, the high point, okay, at 0.6 or at 3/5. Okay, so just a cool thing for you to notice as we are moving forward here. All right. So now we are going to be doing 7 and 8, and then you'll be doing 9 on your own. So we have x minus 3, that entire quantity squared. So we can just set x minus 3 equal to 0. Okay, add 3 to both sides. X is equal to 3. And we know that's going to be a double root. Okay, because we do it twice because that's actually happening twice there. And we could graph that again, and we notice again how we have the top of the parabola touch right there at x equals 3. For number 8, we have the quantity 3d plus 7 times the quantity 5d minus 6, all equal to 0. So that means either this first root or the second factor is going to equal 0. So we take 3d plus 7 is equal to 0 and solve for that d. So we're going to subtract 7 from both sides, and we get 3d is equal to negative 7. Divide both sides by 3, and we get d is equal to negative 7/3. Then we have 5d minus 6 is equal to 0. So we're setting the other factor equal to 0. Add 6 to both sides. We get 5d is equal to 6. Divide both sides by 5. And we get d is equal to 6/5. So we have 2 there. So some of you may be thinking, oh, those fractions are kind of messy. Oh, a little bit. Well, I mean, our first one is at negative 2.3 repeating, and the second one is going to be at 1.2. So, and you can become more familiar with our fractions and decimals as you work with them. So let's go ahead and look at this one just graphed, because sometimes it just helps us to see the graph there. Oops. There we go. I had it all sorts of confused. But you can see at negative 2.3 repeating, and then at 1.2 is where it crosses the x-axis. So being able to convert, this is one of those instances where it's convenient that you have that knowledge of your fractions and converting to decimals or vice versa. So go ahead and try number 9 here on your own. We'll come back and check in just a little bit. If you're joining back with us, you'll notice that our t is equal to negative 4 and t is equal to 4. So this is a rather cool thing. Notice how this first factor and this second factor always look the same. Okay. So, or when they look the same. So we could change this to anything. We could change, so it's 2x minus a number and then 2x plus a number. We could change this to anything. We could change this to 15 and this one to 15. And we'll notice that we have one that's positive, or one that's positive and one that's negative. All right, as we're going through that. And you could even change that coefficient to say a 3. And again, it's going to be mirrored over the y-axis. So we're going to have a -5 and then a +5. So this is one of those special properties when you're working through and solving your polynomials. You notice times when you don't have to do as much work. Anytime you can notice that, oh, I know what that's going to look like because I solved the first one, it makes life easier because you don't have to do as much. I mean, you, you, you kids like to say, "Oh, you're doing too much," and oftentimes, well, yeah, if you don't have that knowledge, you do a lot less. So we're going to get into 10 and 11 here, and then you will do 12 on your own. So we're going to get into 10 and 11 here, and you're going to do 12 on your own. So we have w plus 4 squared times w plus 1 is equal to 0. So we need to set each one of these factors equal to 0. But luckily, we already know that the answer to the w plus 4 is going to be a double root. So we get w plus 4 is equal to 0. Subtract 4 from both sides, and we get w is equal to -4. And we can say, well, that's a double root. And then we set w plus 1 equal to 0, subtract 1 from both sides, and we find that w equals -1. So we have those right there. Now we want to actually see what does this look like when we put that into our and graph that. And I'll leave it open to you to make some guesses as I am entering this. So what do you think that's going to look like? Do you have any guesses before I reveal? Look right there. Looks kind of like a parabola coming up to the x-axis. So we get this, it touches it and then goes away. And then our single root, it ends up going straight through it, and almost like a line. And so we get one at x equals -4, or 2 technically, and another one at x equals -1. So just some cool things going on there. So useful to see how our answers look when they're graphed. Let's go ahead and do number 11. So we have our first factor, g. Well, we get g equal to 0. And then we get 6 minus 3g is equal to 0. Subtract 6 from both sides. We get -3g is equal to -6. Divide both sides by -3. And we find that g is equal to +2. And then we have 6 plus 3g. And similar to what I was saying with number 9, when we start seeing and recognizing patterns, this is supposed to be a 6 plus 3g is equal to 0. We subtract 6 from both sides. We're going to be able to think ahead and know this should be g equals negative 2 because we have the 6 minus 3g and 6 plus 3g. We start seeing a pattern when we keep going across these. Divide both sides by 3, and we will get g is equal to negative 2. So we get g is equal to 0, g is equal to 2, and g is equal to negative 2. So let's go ahead and see again how that looks when we graph it. So zoom out a little bit. So when we look at this, we right there see that it crosses at x equals negative 2, x equals 0, and x equals 2. So we get to see what that graph looks like when we do that. I mean, it has quite a few other features there, but we're focused right there on where it crosses the x-axis. Let's go ahead and you are going to try this last one on your own, number 12. So see how you do. When we end up doing the solution, you can see that our solutions match right up there with our graphing of it. So at x equals negative 12, x equals negative 2/3, and x equals 4, So we did it. Great job. Make sure you take a picture of this and upload it to your Google Classroom if that's an assignment. Otherwise, have a great day from Mr. Potenski, and take care.